Okay, so we're going to start off with the superconductor impulse experiment. So we're connecting together some nickel metal hydrate modules here to power the coil for this take on the pod cloud experiment. And I think Jeremy got into this earlier. Jeremiah, feel free to comment. There's different types of pod cloud experiments. There's also different levels of of things that you can add to this experiment, such as putting it all in a vacuum. That we weren't able to do yet. It is pretty difficult to set up something like that. But we do have it inside of a coil, and we are impulsing it with a large amount of current rather than a super high voltage. And this is 613 joules of energy going into the superconductors via a thyratron. What does that mean?
Oh, sorry guys. Does it look all right? You see that? Also, you want to talk a little bit about your vacuum tube again?
Oh, so this is the thyratron that came out of the
linear.
Yeah, the Berkeley Labs linear accelerator. So this actually came from Berkeley, and they took apart the accelerator and sold it on eBay. And I actually built this this whole setup in order to power it. This entire device is going to be floating at around 35,000 volts. So we have a high voltage Faraday cage here, and there's all different types of electronics needed to power the tube. You have to give it some a static voltage of 6.3 volts, and then you have to apply a high voltage grid that's all controlled via a fiber, basically a light sensor over there. So we can shoot a laser through the side in order to trigger it. It's going to be a pretty cool experiment, and we hope to see the results in a pan on the floor.
Jeremiah, do you want to show us what you worked on today? This thing right here?
Yep, inside there. We've got a brass bolt, taper head Phillips, soldered to a copper disc that's 1 millimeter thick, as wide as the YBCO discs, which are 1-inch discs. And they are bonded at 3 points. So we have a proprietary bonding agent combined with CCTO, calcium, copper, titanium oxide, I think, and nickel silver powder. And then we have just a plain PBO in the middle. And on the other side, we have a mixture of the PBO and a copper powder. And the reason why we're putting the metal powders in this material is the PBO is actually not very conductive. So by cramming them full of these metal powders and sandwiching these plates on the ends of the YBCO, we're able to get some connection to the surfaces of the YBCO, which are ceramic and very, very hard to bond to. And so the other side is just a duplication of the first side, except for the bonding agents between them. And then that's sitting inside of this little chamber here. So I'll pick that up for a moment to kind of show you what's going on here. So earlier, your cameraman right now, Mr. Alien Scientist, cut out these 2 wood discs for us, and we screwed them together with 8 standard household screws to create a nice bobbin, which we wound by hand. This is 13.5 gauge, very heavy build insulation copper wire. And inside of the center is a piece of PVC to insulate the voltage, and then that assembly. You can see the top of the bolt there. The top of the bolt is one of those brass bolts shown in this image. And another one sticks out the bottom. That's our other terminal. And so that makes up the load that we're going to discharge the thyratron with through this through the output of this capacitor, and just cram as much current in here as we possibly can at superconducting temperatures. Now we have to have the magnet on for the time that it's going in transition of superconductor through its phase of not superconducting to fully superconducting, so that it locks in the field created by this electromagnet. And that's what those batteries support. They're going to supply somewhere around 30 amps or so into this coil for about 1 minute during that transition phase to lock the field.
Sweet. These batteries, by the way, are straight out of a scrap pile.
And what are we using to take measurements? Where are we just going to look for observable effects, any kind of observable effect at this point, and then before we set up anything to take data?
Right, because this is it's such a fringe type of experiment, and there's so little known about exactly what makes it work and what doesn't. Now multiple laboratories have attempted to replicate this work and have failed for one reason or another. And so seemingly the only people that can get this to work are the inventors themselves at the core and pod cutoff. So this is more of like an early combination between core and pod cutoff, because we're not using core's proprietary mixture of superconductors and Josephson junctions. We're using more of a Alzofon-style mixture where we have 2 different superconductors where Josephson junctions are formed between each plate and the connection between the 2 superconductors. And also by toggling off, we're using a slightly higher voltage, 35,000 volts in this case, instead of before it was much lower, 9,000 or so. So we're going more on the high voltage side because we have a virus drawing, which is giving us that voltage rating, and because we're going to get a little more current through this thing at a higher voltage.
Bill, we're trying to put together the toggling off demonstration, and we are literally minutes away from doing this.
Yeah.
Toggling off core. It's hard to call.
I'm not really sure what we're going to call this, but it is what it is. You'll see all the components, and you call it. What's today's date? January 6th. It's a January 6th, 2021 experiment. Jeremiah, ready?
We're going to get some high voltage armed up here in just a moment.
How about I test the electromagnet first?
I would highly recommend testing your circuit first.
Okay. I'm pretty sure it's going to work. But,
I'm pretty sure it is too. Here we go. Try again. So you can see the field is going through there. We're pulling about 35, 36 amps right now, which is not bad. That should create a sufficient field to
how many turns
polarize.
is it?
I have literally no idea. As many as I could put on there by hand until I ran out of space. Pretty much.
Okay. So it is what it is. Now all we got to do is put in the liquid nitrogen and get the high voltage going. So we need to move this to the center of the room. So
All right.
just give me a little space.
We just want to confirm that we measured and actually, definitively measured. And so they probably weren't actually, were actually made several times before, but we actually never detected that we're actually very done with the measurement of this 95.
I like a thermos full of liquid nitrogen in the morning.
Because now we are able to
liquid nitrogen. It's almost
detect
full.
a lot of these condensed matter states.
That's gonna be enough for the entire night. For now. Back.
Yeah, that's better.
That's your switch to turn it on and off, right?
Yeah.
You're just shining this light.
I can make it a little bit more sensitive because right now we have all this light coming in.
Right. So what is it with these materials? Like, so like there's different densities, and then
Yeah.
the air density of water is different than air, and the density of the material also is changes the speed of light of them.
All right, we're gonna run it.
All right, we're gonna run this. Are you guys ready? Bust out the liquid nitrogen. Let's get ready.
You ready?
Okay, that thing's on top.
They are wearing safety glasses off camera, just so you know.
We're gonna put those on later.
So he's pouring that right into the PVC pipe. It's going to get right down inside there and cool down that superconductor to our critical temperature. Once it hits that critical point.
I guess I was lucky. My chamber has not been tested yet, but it apparently is holding the liquid nitrogen and out.
Power of the electromagnet.
Okay, here we go.
Okay.
All right, now let's fire a friggin' blast through that thing and step back. Everyone step back. Let's fire something through.
We have to wait. I'm just gonna sit here and watch it to see if it leaks out or if it actually.
You can see it coming out the bottom a little bit here.
I'm not sure if that's coming out the bottom.
Yeah, it might be. I don't know where it is coming from. I can
Well,
see.
it is. It is. I feel it. A little bit is coming out the bottom.
Okay.
It is.
Okay, let's just do it.
No, we still have to cool it down. It's still not superconducting. We're losing it.
Okay, so just get on the high voltage. The high voltage ready. And we'll do it.
Yeah, let's pull it up all the way. Yeah, look at we're seeing it in the tray. We're losing it now. Now it's actually opened itself up. I hope this is enough.
Okay, we're generating heat here from the coil, so we got to really do this fast.
Well, as soon as it's got to stop bubbling, otherwise we know we haven't hit superconductivity.
We're getting there. Definitely getting there, but I don't think it'll stop bubbling because we're generating heat.
It should be not bubbling from the inside.
Okay.
I don't know how we're going to tell if
It looks like it's bubbling from the outside. I think it's ready. Just go. Just go. Just power it up.
Okay.
It's fine.
Stand by.
Wait.
Pull it up and then all clear.
All right, we gotta wait for that. That liquid's all moving on the bottom now.
Yeah, we gotta stop that. We gotta turn off the light over here.
Put something under it to catch that.
That's okay. It's still got enough in it to actually go through the process. That's fine. The smoke might be blowing away too. That could be kind of cool, Jeremy.
You have to get the.
Don't worry about that. Don't worry about the catching that. Just let. I mean, the smoke on the tray there may actually be useful to analyze whether it's working or not.
Okay.
So let's just zoom back so we can see both. You can't be you can't be anywhere near that. You have to
I want
weigh
to see
that.
both.
This is a high power pulse.
Oh, yeah,
I don't want that camera anywhere.
No.
Okay, we have. We're way buried. We're still good.
Okay. All right, we're watching.
Just a little more.
Just a little more, and then we're gonna fire it. I'm gonna see if we got any effect on down there
Okay, it's
underneath.
filled up. Okay. Whenever you're ready.
Stand by. We're gonna start out at a little bit lower voltage. We're gonna go to about 5-6 kV.
1 second. Let me get a close up on this.
Stand by. Give it a charging current. Oh wow, that's a lot of.
Oh, I can see that. That's cold.
That's 10 kV. And stand by. We're gonna try to trigger it. This is at only 10 kV.
All right, safety glasses on.
Ready?
Ooh. Whoa.
That's why I said safety glasses on.
Powering down. We may have just blown our top plate off. We're gonna find out in just a second.
Oh my God. Okay. Was there any shake though on the water before the shake of the
I didn't even
explosion
see, man.
Oh, we shattered our whole container.
I jumped a mile. We
happened? Oh my
shattered
God,
that
look
whole.
at that. The container just fell apart.
Yeah, it
Please
did.
tell me you were seeing the water on the camera feed though, because I wasn't able to look at that. So don't
We
know
could.
if
We got it on the camera.
Wait,
feed.
is
I'm
this-
like-
Okay, so that concludes that video. Jeremiah, are you there?
Yep, just got myself muted in the background so we don't get ringback or feedback.
Oh,
These are wonderful videos, by the way. Thank you for putting these out there.
They're the raw experiments. So unfortunately, we did go back and post analysis and frame by frame reference to see if we had the effect, and we did not. We had terrible bonding between each of those pieces. The bonding agent that we came up with was totally unsuitable, and it turns out that there's no way to have the thing hold itself together. It's got to be under significant clamping pressure, which is one of the things that we'll have to change next time. That whole entire stack, just because the current flowing through it, it would tear a metallized plating right off the surface of the superconductor. So there does have to be enough downward pressure to hold that block together. And also the container that I was in was pretty terrible, leaking liquid nitrogen. We had just a little bit of time left over to run the experiment, so we kind of pushed it together at the last minute, but we do have intention to keep on going forward with this and increasing the quality of the experiment until we have reasonable measurements set up. It was a good practice run, though, and we learned a lot doing it, so we're glad that we actually pushed it through instead of waiting.
all right. I'm pulling up some of the pictures from the from that experiment. I'm just trying to find them. 1 second. We had the actual frame by frame pictures. 1 second. Okay, there we go. Now, can you all see that?
Looks good.
You can here. Let me share. You can see this now. 1 second. I need to figure out what I'm sharing. What can you see right now?
Well, now we see you navigating your folder system.
Okay. No, where was that? There we go. APEC 2020. There we go. And okay, do you see the picture?
Yep.
Okay, perfect. This is a frame by frame analysis of what we saw. Oh, it's not giving me the next picture for some reason.
Yeah, you'll get it.
It's supposed to be option. No, it's not letting me do that.
Windows.
No, this is not Windows. This is
This is
Apple.
the Mac?
Yeah.
Oh, you've got to go to quick view then. Two finger click, right click, and quick look. Then you can use your arrow keys to scroll up and down through those pictures.
Okay, there we go. Perfect. Let's see if I can make that full screen. This little guy is always in the way. There we go. Okay. So, oh, it doesn't
You
like
made it
me.
full screen and you isolated the image again. Yeah, unfortunately, quick look is sort of a preview function only, but it does allow you to scroll through. That's fine. We can see it.
So this is the first frame that we got of the impulse. So strangely enough, when it's when energy is actually traveling through, you can see that through the light on the thyrotron. There was nothing happening, or it didn't happen that fast. The camera is only capturing around 30 frames per second, so this is hard, widely inadequate to actually capture impulses of these speeds.
Right.
So,
What we can see is that the electron cloud is firing through that thyrotron, but the wire hasn't shifted yet, showing us that even though voltage is present across the superconducting junctions, the current hasn't really started to flow yet. So in the next frame, I believe we'll see the wire move. Yeah, and there we can see the current is flowing. The entire wire is shifting, indicating that the magnetic flux loop is got current flowing through it. But unfortunately, what we don't see down on the water tray is any kind of surface distortion or aberrations, telling us that if this was a powerful gravity impulse beam and we had succeeded, we would definitely be able to see it on the surface of the water, and we cannot. So this was a failure, unfortunately, but a great learning experience nevertheless.
well, we don't really see the water that well. It was a failure in the setup, but I agree. I don't really see much going on there. That little white speck you see here is probably just liquid nitrogen flying off toward the camera. Did make a pretty nice explosion, and we spoke to our Professor Emeritus, Professor X, as he prefers to be called, and he recommended a whole new bilayer setup with the superconductors, specifically the Josephson junction setup, that it has to be perfectly flat. And we're going to try that again in the next iteration. We have all the components, so trying this again is just a question of rebuilding that little pipe and putting the superconductors back together properly. But everything else is still here. Nothing was broken from this assembly.
Except for the holding container.
Yeah, the holding container blew up, and I'll get to that in a moment. There you can see the pieces of the holding container coming apart. And liquid nitrogen is spewing everywhere. I guess that's the light from the camera. Oh, this is the copper disc that we ended up with. You can see there was some burn through marks, which tells us that there was paths where it preferred to go through.
Yeah, so my suspicion on what we got here when we inspected this later is that after the flux started to flow through that system and it basically tore itself apart because it had no downwards clamping pressure to keep it together, there was still enough voltage left in the capacitor where it was able to arc off the surface instead of being more distributed by the electric fields. And so this would have probably occurred as the discharge was finishing up and as the assembly was flying apart, but the voltage was leaving the capacitor still. And you can see exactly where that break point is. As Mark pointed out here in this picture with the PVC, you can see that just about the middle of the tape mark there is the top of that assembly. So this would have been right centered where the superconductor was and where the electromagnetic field would have been concentrated.
One thing I'm wondering is what could have caused such a force on the sides? I don't think this is merely the expansion of the
liquid nitrogen. It could be, though. I mean, the truth is that when you turn something straight from a liquid to a gas in a fraction of a second, there is going to be a lot of pressure there. So I could see that happening with the liquid nitrogen.
That is true, but if you look at the pictures from earlier, we're not really looking at that much gas. It's mostly liquid nitrogen that came out. I mean, look at that. That's liquid nitrogen. That's not gas.
Well, that's even more pressure because the liquid in its liquid state is going to be even less compressible, so virtually incompressible. So all that pressure for the tiny amount of gas that is in there is going to have no place to go except for to push the liquid against the sidewalls and break it.
Right, but where's the pressure coming from?
It would come from the expansion of the liquid into a gas state as all that capacitor energy was
Yeah,
flowing through, forming those sparks.
There would need to be gas in order for there to be expansion. Water is less compressible than gas. I understand that, but we're seeing a lot of liquid over here. This is something that we should really discuss and look at with a high-speed camera and subsequent experiments. Also, I think it's interesting. It would be worthwhile in a future experiment to put some sensors along the horizontal line alongside the Josephson junction or whatever you would call it. See if there is any impulse going sideways as well. Maybe we are creating gravitic impulses, just not being concentrated correctly. So there's a couple things to look at. But yeah, I do see mostly liquid nitrogen here. I mean, if you were to spill liquid nitrogen, this is what you would get. Another thing that I didn't consider though is that PVC at these temperatures is very brittle, so it might not take that much power or pressure to break it. So I'm not really sure on that, but there is a possibility that it got very brittle at that temperature, and anything could have cracked it.
Yeah, I really don't think that we've seen anything special there, but I mean, we did see the effects of discharging a large amount of energy in the form of a plasma arc through liquid nitrogen, and the consequent expansion of said liquid nitrogen into gaseous nitrogen. Either way, it was a heck of a learning experience, and at least we have something to go off of next time. We're not flying in blind.
Right. I don't see much liquid gaseous nitrogen here, but whatever. That's to be determined. But definitely for the next experiment, we do know what we should be looking for and how we can try to do this better. Although if anyone in the audience has any suggestions of what materials to use for these super low temperature dielectric materials to hold the superconductor, I think this was a 1 1/4 inch PVC pipe. Is that correct? It was 1.5 inches. I'm asking you, and I actually have the piece of pipe right here, but it was about 1 1/4 inches, I think. There's another angle of it. So it broke right where the superconductor was.
Yeah, that's correct. In the next iteration of this experiment, a lot of things are going to change. First off, the entire assembly is going to be rebuilt with proper Josephson junctions, which we'll have to spend a lot of time building. We'll probably spend a good 2 days just making that junction correct because it's got to be so precise and so perfect, which means sanding the surface of the superconductors down to practically a polished finish and having them absolutely flat and parallel. And then finding a material that's already preformed that's going to give us the correct spacing. In fact, we may not actually need to bond it as long as we have enough pressure holding the stack together. That's how an SCR is assembled, and it works just fine. They're not bonded, they're just pressed together, and they have to operate under pressure. So that's the first thing. The second thing is, the water tray cannot be on the same mechanical assembly as all those moving parts. So it's got to be placed some distance away, and we need to cover it up and isolate it. The third thing is there needs to be a reflecting grid that we did try on a later iteration of the same experiment a few days later, so that we can clearly see the surface of the water and even the tiniest distortion. So we'll have a dedicated camera stuck directly on that water tray. So lots of changes need to happen, and we're well aware this experiment was improperly set up, and we do have some ideas on what we'd like to do. But of course, we are really open to suggestions, especially from you folks, because this is the most educated and qualified audience, I think, to really give us advice, and we're very much open to listening to that advice.
Okay, if anyone has any comments, let's open up the floor to talk about this. Anybody?
Yeah, I would just like to say good work. Actually, this is one heck of an experiment. I mean, it's not always right. I mean, I think one of the fundamentals of science is you're not going to always have a positive result, right? Most of the time you'll have a negative result. But what is interesting is it's obvious that you guys have done a lot of work putting this together. And it's, I love the fact that you guys are doing hands-on building, right? That's what this is all about. And then I think everything that you've mentioned for the next one, isolating it, right? Mechanically isolating it, trying to put a cover over it if you can. I just typed in chat, maybe something to maybe consider would be like if you were able to reflect light or a laser off the water, it might show variations in the surface, you know?
That's a good idea too.
So, but I mean, overall, I think this is a great experiment, you know? I mean, again, this is a garage build. This is what it's all about.
Exactly. And I think, if there's no more comments, we can move on to the next experiment, which would be the electret anti-gravity build. I'll make sure I am sharing the right screen again, because we've had that problem in the past.
Yeah, this is one video of our attempt, our 20 something attempts at doing this with many different formulas. This is just a hot process design, but we tried with all nature of waxes and dielectrics and mixtures. So in this case, you're going to just see plexiglass.
Right, the acrylic attempt, and then we're going to go on and do a couple experiments with it, which are kind of cool, and then we finally kick it off with the anti-gravity experiment that Ron Kita talked about. And if Ron is in the audience, we want to get your input on this as well.
Go for it. What do we got here? Well, seems to cool down.
There it is, one ugly piece of very warped plexiglass, but generally not bad in the center area. In fact, it's kind of like an art piece. Anyways, it ended up working out pretty well. You can see the profile of the pieces that were set as the electrode plates. And the big question I have is, was this actually hot enough during the making of this electrode? That's one question we do not have an answer to yet. But supposedly, to short the plates, there's plenty of static on there. That's
It's a good sign.
yeah, it's a good sign. It is remaining charged. Wait a second here. Yeah, there's more static on the surface, so this is a good sign.
I feel a little bit.
Of course, there's probably all kinds of charges around here that are drifting back in and being neutralized. So I guess it's time to short the thing out and put it in some foil and see what it does. We do have the other one that we made.
Okay, so we're here at the Falcon Space Alternative Engineering Conference Lab, and we created our first working electret. It is made out of acrylic, and you can see the sides of it are not the electret's in the center over here. An electret is basically a magnet for static electricity, and we have it covered in aluminum foil. And watch what's going to happen as I bring the aluminum foil closer. It grabs onto it like that, holds that in place. It's holding it against the force of gravity coming up. The polymer are oriented according to the static field that was applied while it was created, which was around 50,000 volts.
In this case, we were at 48.5 kilovolts in order to make this electret. That's made of a 1/4 inch piece of acrylic, 7 inches by 7 inches square. Severely warped on the edges, but the center came out very, very nicely. And that's perfectly all right, because that's really the area that matters. And we could trim all the extra junk off. Otherwise, it's quite beautiful, but it does seem to be maintaining its electrostatic field. And even now, nothing connected to the other side. You can see it's still electrostatically attracted to just that ground reference point for the foil. And if not for the foil being, 2 layers thick, it could probably hold it upside down. So this is not bad. It does seem to be holding an electrostatic field. And this is a pretty good sign. So now I think we just have to figure out how we're going to do our gravity test experiments.
You're playing with electrets. Now, the reason why it's dark in here is because we're going to show you a little experiment. What happens? We can't really see the light bulb. It's kind of dark. There's a light bulb, a fluorescent light bulb that we are going to attach. Oh, you can see it flashing on and off. Now, what is happening here is we're moving these plates up and down next to the electric field created by the electret. And that converts our mechanical motion energy into electrical energy. And that allows the fluorescent light bulb to light up.
Now here's the interesting thing. If I only lift this plate a small amount and touch the bulb, it only lights a small amount. If I lift this plate a very large amount, it lights a larger amount. So there's a distance at which it's, diminishing returns, but just a little bit away from the plate, you're not really going to get a huge amount of charge change because the electric fields from the plate, from the electret itself, are still present in that area. So at least a spacing of 1 inch lift is sufficient to separate the surface plate from the electric fields and provide charge. But it's surprising, just how much charge you're able to draw off this thing. And another interesting observation. So I'll move the electret plate around while keeping it grounded here. And now what's going to happen is when I lift this up, you should develop more charge. An even brighter flash with the visible spark. Not bad. Much more effective than simply a conventional electrophorus.
I'm going to show you what's going on with the light on, just so you have an idea. The fluorescent bulb is not attached to anything other than that plate that we're moving up and down the electret, above the electret. The electret, of course, is that piece of plastic. Acrylic.
You can hear, if you listen very carefully, you can hear the spark discharge. Charge. Discharge. Charging. This is probably going to snap to me. That's probably going to hurt. Didn't hurt too bad. I can deal with that. Okay, so this is the issue that we're having. Here is a classical problematic digital scale. And here is a charged, not electret. In one direction, we have 63.308 unstable grams. If we flip it around, remember we're comparing to 63, now we have 62.252.
Antigravity!
That's right. Flip it back around, but what do we have? 63.2 and flip back around and 62. Wow, look at that. We have a whole gram of difference between one side and the other.
It's now, practically floating.
Yeah, now why is that?
Electrostatic.
It couldn't be because, there's charge on the surface that's causing this maybe to be attracted to not only the scale and its surface, but the table beneath it.
You think?
Yeah, because if we do, some more of this sparking and arcing.
You're crazy.
It is what it is. So
that doesn't hurt.
Of course it hurts. Just used to it. Okay, but here's the issue. So we've seen a gram of difference before, right? Now what do we have? Now we're spaced away.
Ooh,
look at that. Okay, let's see. 62.277. We'll flip that over. Try not to tip it over this time. Yeah, this platform, not made for this. Let's see. 62.34, 60, let's see. 62.34, look at that. Pretty much the same, but we get rid of that. And now we're close to the table. Look at that. We lost almost 4 grams. It's amazing.
Magic.
4 grams just by placing it close to the table. So what we're really showing here is an obvious false positive, and one that we've seen many, many times on YouTube replications and videos and all sorts of stuff. And we thought that it was important to point it out here and sort of poke a little fun at it, because this is a mistake that happens way too commonly, and it's even tricked some members of our research team a few times. So at least now we can all take a look at it and know what not to do and how to recognize a false positive when we see one. This is the electrostatic attraction to the table and the scale, and you cannot use digital scales, or if you dare, your sample has to be several feet away from the digital scale at the minimum and all other surrounding surfaces to try to null out those attractions.
Statics. Here's our pile of electrets, and they all work, and they do exactly what he's showing right here with that piece of silicon. They're just permanently static or semi-permanently static.
But in either case, we have a measurement error issue, and that measurement error has everything to do with the surrounding surfaces. If we place this on suspension strings evenly distant between the ceiling and the floor, we'll get the same measurement in both directions. And that's the problem.
Exactly. Thank you for the demonstration.
Okay, Jeremiah, I heard you talking during the presentation. Were you trying to say something? What was going on?
Yeah, did I not come through? I guess on your end, you probably heard the audio, so I'm not sure how much of that came through. Yeah, basically, we're just poking fun at one of the false positives that we see all the time in many other applications of people looking for strange or anomalous effects involving electrostatic fields. And that being, you really have to put huge distance between your test sample and your scale and all surrounding surfaces, or you're going to get false positives due to just standard electrostatic attraction. And it needs to be avoided. We'd like to see this mistake stop completely, also amongst members of our research group.
Okay, is Ron Kita in the audience? Because he actually talked about.
It looks like he dashed.
Oh, he dashed. Okay, darn. Because I was really hoping to talk to him about this, because he was the one who put us up on it.
Well, we still don't have any of the same materials that he used yet, and we do know what we need in order to build what he's got in his patent, but those materials are highly toxic. So until we get better training in dealing with these toxic chemicals, I think we should probably just stay away from them before we poison ourselves by accident.
Oh,
So I know we didn't do what Ron had prescribed, but we did at least investigate the idea of electrets and possible gravity attenuation. It seems to be not as simple as simply having an electret.
right. Right. But we did try this also with an electret, right?
Yeah, we tried this with an electret, and we also tried this with just plain old static fields that were charged on a dielectric that was not an electret, and we received basically the same results in terms of mass measurements.
Okay, let me try to minimize this. Okay. We have one more video to show, actually quite a few more. Let me do a share screen, or you know, I'm going to pull this up first. Okay, so this is the gyroscope one. This is something that people were pretty excited about. We went through several iterations, actually, of this experiment prior to getting the results that we got. One second, I'm going to have to share the video. Bear with me a moment. Okay, there we go. So this is the power up of the first device, and there are 3 prototypes that we go through over here. And this video, I think, is 17 minutes, but it is very informative. You can see we tried different types of orientations and movements of the gyroscopes and got different results. So here we go. Okay, this is our first power up of the Gamble device gyroscopes. We had to add in some resistors over here in order to stop the gyroscope motors from overstressing the connection point.
That looks crazy when that turned on. Probably your accurate reading there. That could be.
Yeah, I'm getting 20,000 on all of them.
Yeah. Having a little trouble.
Yeah, they're pretty close to each other. Right now we're going to try the swinging gyroscope, and this thing sounds really cool when you power it up.
Yeah, let's turn some more shit on. I want to see this. This is great.
You can hear the gyroscope slowly turning on. We had to put a row of resistors in there because they were turning on too violently when we just powered them up straight. So now it's running through the row of resistors. When I turn the resistors off by shorting out the circuit, you're going to hear them go into high gear. 3, 2, 1. I'm going to power on the remote control. And now we're going to go power on the servos. 3, 2, 1. There we go. Just stabilize the device. Like I mentioned earlier, this device is not very stable. The gyroscopes are being held by these tiny little servos, which are not adequate. But we will try it regardless.
Yeah, I can see a lot of instability in those motor mounts and the servo mounts. Oh, that was a little hyperextended there. You got some collision going on there.
A lot of shaking going on here.
Again, we need to eliminate that static friction point there to make sure it's not just pushing off of that as a pivot point. There's any kind of place in the system where you can have a buildup of static friction, and then a sudden release of static friction will create a push point where you can push off of.
Stabilize it a little bit.
But this is interesting because it has turned, it has rotated about 30, 40 degrees so far. There, it just rotated backwards, and now it's also colliding with the pin in the center. I think they need to be mounted.
They need to be mounted differently, yeah.
So we'll have to.
This is a work in progress. I wasn't really expecting
rework on that one, but yeah, that's cool that you set that up. That was cool. People want to see stuff like this. They want to see us working on it, at least building up. I mean, at least we know what's wrong and some of the design flaws in the system. And if anyone has any recommendations, draw us a sketch and send it to thealienscientist@gmail.com. Thank you.
It is kind of working. Look at that. It depends on how I pulse it.
Is that actually doing it?
It's actually working, yeah.
Well, that's
It
interesting.
depends on how you pulse it.
It kind of is working, isn't it? It does actually look like it's working. That's weird. I wonder if it is.
All right, now it's working.
I know how tight that torsion pendulum is. If it's actually pushing past that, that's pretty good.
You want to try it? I was just using the right control. You move them together.
So the goal is to move it really quickly in one direction and then move it slowly back to the next.
Stop that.
We have some kind of experiment.
So the full movement is down to the bottom.
It almost seems like it works, doesn't it?
It almost seems like it works, doesn't it? This is very interesting.
I'm telling you, man, I'll just die if it's
You can't do that. You can't do that.
propulsion.
It's not strong enough. It's gonna break.
If it's general propulsion.
Yeah, it's just gyros, but the best way to do it is with the TR3B. A torus full of rotating mercury.
You just gotta move them together.
Right?
Point.
Jesus. Could you imagine?
I hope it's not something that simple. I don't know, man. I really want field propulsion. I want field propulsion to throw in parts. That's the ultimate goal.
You know, that goes against all the stuff that I think it is.
Check this out. It is working. Tom here is at the controls. He's trying to use just one gyro to make to get it in resonance with the device. I don't know if that's actually field propulsion if we're going in resonance with the entire setup. But we are getting.
Wow, he's nudging it forward, inching it forward.
Just one gyro is being controlled right now. Tom, what method are you using to control the
whatever. Try to produce a torsional moment in the entire system. I assume the correct.
All right, keep on doing what you're doing, Tom.
I can see what he's doing. He's timing the pulses with the frequency and the pulses.
We just killed its forward momentum. If you can get that thing going again in the same direction, it's very impressive.
So we just killed the its forward momentum. So if you can get it going forward again in the same direction, then we'll be impressed. So I just want to show real quick to line up.
Moving in the other direction now.
It should be possible to move it equally well in either direction depending on the speed change between the forward and the reverse stroke.
It's designed to be moved diagonally.
So Tom's sitting here with the controller.
No, the other
Why don't you
diagonal.
hold the controller up a little bit
This
higher.
diagonal.
Just right there. Yeah. That way people can see your control. We got the servo motors in the device up there. Hooked up to a RC.
Okay, so this is how it's designed to work. It's designed to be ran like that. We might have some. This guy looks like it's about to fall off.
That doesn't sound good.
No. Again, we are running into some technical difficulties over here.
Can we postpone this one? Let's try.
Yeah, I think I'm going to power this one down.
Let's power this one down. This was I want to get this set up with a little bit better motors there, a little bit better coordination on the and maybe a little bit bigger spacing so they're not hitting each other too, or something.
Yeah, we definitely need to rethink this experiment. We actually have parts coming in tomorrow, stronger servos, and we picked up some aluminum bracket that we're going to be using to attach to the gyroscopes instead of these little spindly arms that it came with. They're not sufficiently strong enough to hold the device, but we have seen some movement over here, so it is very promising.
Damn it, Mark,
we're
I
gonna
told
be-
you not to get into the controls.
We're going to be going forward. We're going to be moving forward on this experiment for sure. It kind of sounds like a UFO now,
Right.
like a flying saucer. So
Well, you got the sound right anyway. Now you just need, the anti-gravity part.
yeah.
Yeah.
Okay.
For the record, this is prototype
We're
B.
going to test the Vimana craft, prototype B. Now we're going to power it all up. Gyroscopes are spinning.
Now, as they come up to speed,
The voltage in the system should rise because the current will drop. Right now it's going through the resistors. And soon we'll get the servo action going.
Those gyros sound like they're really in sync. That's excellent.
Lots of shaking going on there. Let's try a different movement. It's definitely wobbling around a lot.
whole pendulum is swinging. I'm going to fast forward a little bit to the okay, so yeah, we tried all different iterations. We kind of got some positive results with the 2 gyros. Over here,
Well, I
we're
mean, take a look. Here we go.
4
I thought it was
gyros.
just something there. Well, here's the motion. So it's pretty straightforward, and it's just on the one axis.
Sounds like bagpipe music.
Actually, there's a natural oscillation too. It's also trying to correct the servos.
Interesting. It is kind of like rotating around a little bit, pushing it a little bit, you know? So if this is the kind of motion that we need to do, and we can do it with these like 2 little gyros, and it's propelling this thing a little bit, right? Now imagine if we took the same kind of motional effect, and we started doing it to all the little spin orbits of these electrons or atoms in the surface of our spin coating, or smart skin, right? So we had a smart skin full of all these sort of atomic gyros acting as a surface mediator for this, you know, assuming that gravity and these interactions are a surface phenomenon. And then we have all these sort of electrons or these surface particles moving in this sort of coordinated motion. We could, like, maybe it would be a much more efficient way to atomically paddle through space-time, you know? Well, we're starting to,
Yeah, it likes to really chill,
balance
man.
and stuff, man. Anyways, this is really cool. I want to break this down because I want to get.
Okay. Jeremiah, are you there? Why don't you unmute yourself?
Yeah. I'm still around. I had to step
Okay.
away for a minute.
So you were with me with the process of building that whole thing, and we tried it. I wouldn't say it was conclusive that we're definitely seeing like massive forces, but I did see some strange movement, and I'm kind of concerned with the whole pendulum setup and how that was set up.
Yeah, the cogging motion that could be contributed by the bearing there is no good.
Yeah.
It's just too crude of a setup, but at least we know what not to do yet. And it did show us something interesting at the minimum. I mean, whether it's cogging or not, at least it moved. So now we just have to eliminate all the other possibilities, all 15 of them, and try again.
We would also have to figure out the correct movements that produce the maximum thrust, but that's all done inside, you know, in the remote control. So that's not that too big of a deal. Another thing we can show, we have the March generator. We can show that we have a video of that shooting a spark around 4 feet. That was one of the things that we built here in the lab. Here, let's show a video of that. Let me see if I can get the share screen going again. Share screen. Okay, share, there we go. Okay, we're here at the Falcon Space Lab and we're testing our 1 megavolt March generator. We have our defibrillator over there in case there's any problem. And when you're ready.
Charging.
What's the voltage at?
Going up on 25 kV, and then we're going to give it a little bit to stabilize.
Give me a countdown before you shoot.
Unless it fires ahead of time. we're at 25 kV, and now we'll just wait. Let's hope that it doesn't fire, because it is pre-cracking a little bit. All right, 3, 2. Well, that wasn't supposed to happen. So we still have something we're gonna work out. Before I'm gonna try to fire it this time. On the edge of the board where I need to adjust it. But I guess I can reclamp to that thing and readjust that, because this thing is kind of a sharp point. I can do that too.
We get a good shot at the
This
end
wire.
of this.
Yeah, that's
I will let you know. Where to hit one more time.
Okay. That's for that. There was some problems with it. And we did eventually get some large sparks going on.
Yeah, it's a shame that we lost one of those capacitors, or that we didn't catch one of those in the testing. So we still got to figure out exactly which one that is. But at least we're getting up to about maybe 600,000 right now. We're still far shy of our 900 and something thousand volts that we should be hitting.
Right. We'll
get there.
Did you want to do anything about the?
It looks like Bandurk had to go, so I think I'll save that. I'll email him privately and send him some pictures of what I'm working on. He gave me a bunch of advice today too, that outside of the public and private chat. So that's all stuff that I'm going to apply. I did a lot of things wrong on the Bandurk replication in the first case, and among them, I guess I can show some of this stuff here real quick. I don't know if you want to pin my video.
1 second. I'm just going to do the Marks generator firing.
You have it? Okay.
Yeah, it's up right now. It should be share screen. Can you see it?
Yeah, we can see it.
Okay, there we go.
okay. Test in the dark. Let's go. Marks generator, 1 megavolt. Oh, like 750 now because we haven't spaced everything out properly yet.
Yeah, that was supposed to fire. All right, 3, 2, 1.
Nice.
That thing fired up again.
I saw a secondary spark at the end.
At the end? What do you mean?
After it went, there was a second spark in the base.
In the base.
Yeah.
You got it on video, so we'll have to take a look at that.
So that secondary spark ended up being a problem with the resistors, and we had to add in a second row of resistors for the feed line.
You know what the real shame is? Anybody watching this probably didn't see any of the sparks in any of the videos, because the frame cutting from Zoom is so extreme that being that the discharge is 1 frame long, I have a feeling nobody really was able to see it. We'd have to freeze frame. So something to note in the future again, Zoom definitely needs the freeze frame in order to show everybody what we've seen.
Well, I do actually have that freeze frame picture. Let me see if I can find it. Where's the Marks generator? There it is. It's kind of hard to see all these pictures, but you can go ahead and start sharing the information about Bandurk. Do you want to share the screen?
Yeah, I think, I'm not going to share my screen, but you can pin my video so that can go full screen.
Okay, so I'm going to see how I can do this. Okay, there you go. You are pinned right now, and I'm going to mute myself as I get this experiment going. We're going to be doing easy Alzofon right after this.
I am pinned right now. It looks like you're still full screen right now. You're still the speaker, it shows.
I'm seeing you as the
Well, I don't know. Maybe it's different. Maybe it's not showing me because I'm the host. I can just start showing this stuff. So this was one of the assembly pieces for the first generation Bandurk device, and here we have here we have our dot product disc, and this has got about 5 grams of tin and about 1 gram of epoxy mixed in on the surface here. And you can see these rings around here, and these are caused by the ultrasonic vibrations that we placed on the disc during the forming of this material to try to distribute the particles out evenly within the mixture. And so it's not perfect. It's not a perfectly smooth surface, and it really shouldn't be. In fact, the idea is that all the charges will get trapped on every little conducting metal particle within here, and because they're epoxy insulated from each other, the charges shouldn't be able to leak off. This was placed behind a piece of 50 kV dielectric and pressed directly against it. This just sort of keeps the charges from flying from the dot product disc over to the cross product disc. Now, we had initially tested, this is the cross product side, with the motor, the power meter, and a small battery cell. So in order to flip this thing on and turn it on with isolated charges, we couldn't touch the circuit, so we just have a magnetically activated switch, which can be triggered very easily just either by blowing on it or with a small stick. And so that gives us a voltmeter display and a current draw in milliamps for how much energy the motor is consuming. And when we apply high voltage, if it was working correctly, we should have seen that motor power go up and heard the RPMs slow down. And we did see a very tiny change, but it's nowhere near what we should have been seeing. So we know that we didn't get the effect that we were looking for. And so this is just a DVD that's been coated to one side with aluminum foil. It unfortunately was not ideally smooth enough, so that was the second mistake. And the third mistake was this disc, as it generates a complex electric field component that changes the geometry or distribution of the charge across the disc. Instead of being evenly spaced away from the surface of the disc, what we'll end up with, well, this thing is rotating and it has a charge, is the charge will be sort of weakish in the center, and as it reaches or approaches the edge, you're going to get a lot higher electric field, and then right near the edge, it's going to cross back down and the electric field is going to die. So to replace this in the new version, we're replicating something a lot closer to what Richard actually did. And in that case, we're using printed circuit board that has several rings cut on the inside. And the reason why these isolating rings are placed there is so that we can solder and place low leakage diodes to farther isolate out charges. So once they reach the outside periphery, the large copper surface here where the electric field component is the greatest, then we can't allow charges to enter back into the hub. Even though the tube isolated, this is just an extra step. So this polished copper disc fiberglass on one side will be able to take 50,000 RPMs as compared to the last system, which we only took up to about 10,000 RPMs. That'll give us a much greater complex electric field component. And the smoother surface should help significantly as well. So that's the next couple of steps that we're taking. We still have a new motor design to go through, and we want to run it off an ESC digitally controlled so that we can get an RPM readout and we can get more precise power measurement draw so we can identify if we actually are getting that loading, that torque loading on the cross product disc. If it loads down, that'll tell us that we're converting our angular momentum into linear momentum, and then we can measure that with a scale or with a meter or with something else. But first, one thing that Van Durk did mention is that we need to measure the field component of the surface of both discs when they're rotating. And so I just placed order for a Coulomb meter, which will tell us the electric field change on the surface of that disc. And that will allow us to fine tune the circuit.
We did notice a change in RPM, or at least audible change in RPM.
Yeah, very small, but it was there.
Yeah, that's important to note.
So that's where we're at with that so far. We don't really have much to show on that because there was a lot of other effects that caused measurement error. There was airflow, the system wasn't boxed up, and there was also the magnetic component of the brush motor having a north-south juxtaposed magnet. It was actually aligning itself with the Earth's magnetic field because of the sensitivity of the torsion balance. So we had to discover just how sensitive that was, and the fact that the motor containing magnets is going to try to compass itself. So both factors that needed to be eliminated, and they can be simply eliminated by flipping the thing on its side and measuring in the horizontal orientation, or measuring in the vertical orientation instead of the horizontal orientation. That will pretty much help us eliminate the geomagnetic field.
Right. Okay. We did notice a lot of very strange effects with that.
Yeah, we did. It seemed to be pulling itself in the wrong direction, according to the Bernoulli principle. Air was being sucked into the surface of the rotating disc and flowing out towards the edges, yet it was actually pushing away from that direction and pulling itself towards the dot product disc, which was kind of unusual. So there's still lots more to investigate with this thing, and we don't exactly know all of what cause the observations that we seen. But and then again, we don't really have good measurements of it yet either. So all that to come.
Right. We also have had positives when there should have been a negative and negatives when there should have been a positive. So it was very strange what was going on. I think I made the observation, I'm not certain of it yet, that the effect was not drawing any current whatsoever from the high voltage. It was merely drawing it from the motor, which
Yeah, that seemed to be the observation. We did have an initial draw from the high voltage. There was the audible sound of ions being flown off the edge, and they eventually stabilized. But all that shouldn't be happening anyways in a properly isolated system. We know that that's a problem. And so yet more things that have to be corrected in the next version. We'll probably have to completely encapsulate the dot product disk so that it can't leak any charge whatsoever.
Right. Okay. So I'm getting the easy Alzofon experiment ready. I'm just going to turn on.
Oh, you're going to do that live, eh?
Yeah. I got the KEPCO power supply going.
Oh, nice.
It turns out it does run on 110 electricity.
Hey, sweet.
And we didn't need to.
Do the 3-phase wiring.
Yeah, we didn't need to do that. I'm going to try to join with video.
I'm going to step away for a minute and hand it over to you.
Okay. Admit. Oh, it should be connecting. I just need call in using internet audio. Okay, I am going to mute myself over here. Can you hear me now?
Yeah, you're coming through loud and clear. Well, you were. Now you're not.
Okay.
There you go.
Okay, so we'll try that again. What we're looking at here is an aluminum flywheel inside of a electromagnet.
Your mobile cam is not the focus of the screen, just so you know.
Okay, so let me add pin. And Tim, if it's okay with you, are you there?
Yeah, I'm still here.
I'm going to make you the host because I can't handle all this, okay?
Okay.
Oh,
Okay.
there we go.
So hold on. Let me do this. Let me spotlight for everyone. There you go.
Okay, perfect. I'm going to do audio off of the computer and we'll do video off of the camera. And we're also going to do video off of the laptop because that's where you're going to see the result. So basically what we have here is there's a small electric motor. It's capable of about 1 horsepower. And on top of it it's connected to this huge aluminum disc, which has been balanced. The aluminum is grade 5052, which is a mixture of aluminum with it has a tiny bit of iron in it and also magnesium. And magnesium and aluminum, according to Alzofon, have very similar properties in terms of their dynamic nuclear orientation. So that's not a problem. A little bit of iron is actually desirable because it allows the magnetic field to permeate a little bit better. Now, according to Alzofon, the effect is supposed to be contagious, meaning that objects nearby also lose weight. So we have a piece of Teflon over here, which is undeniably extremely dielectric and should not integrate with the system at all. And in order to remove any possibility of airflow interacting with the weight, I have a piece of cardboard over there on hand that we're going to place in between the spinning disc and the device once we have it spun up in order to get our results. Now, this is attached to a our little scale over here, force sensor, which then goes down and to our laptop. And this thing's fighting me. And I'm going to open up the screen over here shortly. We're going to turn on a share screen. Tim, you're going to have to enable participants to screen share again so that I can screen share the results of this experiment.
Yeah, no, it should be. Let me take a look. Oh, yes. Okay. How's that?
Okay, I got it. Now, you're gonna have to figure this out on your end. You people probably want to see both angles, but this is the weight of the object right now. It's 5.46 newtons, which I believe is around half a kilo, or a little bit less than. No, it's around 5.4 kilo. Oh no, 540 grams, roughly. And if I lift it up, it should go to about 0, but there is a little bit of weight from that string, so that's where we're going to do residual weight. Trying to get it as balanced as possible. Now I'm going to have to go get a tripod in order to mount this. One moment while I set this up. This is kind of on the fly. So this was predicted by Frederick Alzofon that this would produce some sort of effect. If you're familiar with the ARV, this is pretty much what you're looking at in the center of that ARV, is a spinning aluminum flywheel inside of a electromagnet. You might be pulsing that electromagnet. We have no idea what the specifics are. I spoke with Mark McCandlish and told him to be here. And if he's in the audience, he might find this experiment pretty interesting.
It looks like Mark is not here.
Oh, okay. Give me a second to set up the tripod. Sorry for not having anything ready. I was trying to get everything going kind of last minute. Okay, so first things first. I'll show you, this is the famous picture of the ARV, and in the center of it, we have that aluminum flywheel with the electromagnet coil around it. That's exactly what we have over there. Aluminum flywheel, electromagnet coil around it. This is supposed to create the dynamic nuclear orientation for the craft, which would reduce its weight, allowing the parallel plate capacitors to lift the craft up, according to my theory on that. And we'll see what happens with this. We're going to call this experiment Easy Alzofon, because this is an experiment that anybody can do. It's quite simple in terms of the greater scheme of things. There has been trouble in the past getting the motor started because it notices such a large dynamic load that it has given us a little trouble. I'm trying to center it right now. Looks like we're stuck on something. There might be glue. Oh, the wires have melted. I'm going to center this up. Okay, I'll center up the coil. Okay, it's roughly centered. I don't know if centered is a desirable trait, but we will find out shortly. Okay. That is, of course, the motor turning on. Now, we have some stabilization going on there. So the electromagnet is not turned on yet. So I'm just gonna have to like pre-spin the plate a little bit so that the motor can catch. Otherwise it does this. Okay. technical difficulties here. I've had this problem before. There we go. Now, as far as RPM goes, I'm not really sure what we're looking at here. We do have an RPM meter, but we haven't put a sensor tab on it. And this is at only 10% of throttle. I can throttle off of it. So first, we're going to go to full speed without any electromagnetic field going on. About 40%, 50%, 60. Full speed. That was full speed on that motor. There should have been no weight loss, and that's probably what you saw. Now I'm going to do just the electromagnet as a second null test. There is a lot of built up angular momentum in this disc. I'm trying to slowly and gently slow it down, so we don't have the two components going on together to get proper null tests. Okay, there we go. Now I'm going to power up the electromagnet, and we will show you the Gauss reading as well as the current reading from the electromagnet. There's a Fluke 365. Now let me see if I can zoom in on those two. This is the TD8620. We're going to read them in Gauss. Just give me a second. I'll focus in on the results. We can look at the strength of the magnetic field right over here. Current and the strength of the magnetic field. So let's just zoom in on that. Okay. Can you guys see that?
Yeah, the angle isn't really that great, but you're probably going to spend more time trying to get the right angle than just to read off the numbers. So just tell us what you see.
Okay. Current's 1 amp, 3 amps. We're at 5 amps. Uh, 10 amps. 20 amps, 25 amps, 28, 29. Okay, so we're at 30 amps, and I'm reading in the center about 240 Gauss. Toward the sides, it's around 400. In the center, it's around like 230, 240. Pretty laminar across the entire plate, probably a difference of 20 Gauss from the center to the edge. It also depends on your orientation, but we should not be seeing any difference in the weight. I just turned all the power off. We're at 0 amps. Now I'm going to power it up to full power. There is no change in weight. Okay, so we have our null tests, and if the combination of these two, spinning it up and the electromagnet produce any force, we will undoubtedly know that something is going on. Also, I noticed that we did this test without any barrier for the airflow. We did the null test without any barrier of the airflow. So I'm going to take the liberty of just leaving that out of the equation. And We'll bring this in a little bit closer, so if there is any effect, we'll have an easier time detecting it. Okay. Okay, there we go. Now I'm just going to spin up the disc like we did last time. And here we go. No. Can you catch? Okay, first we're going to run it at around 60% speed. Okay, powering on the electromagnet. 3, 2, 1. Stop. No weight loss. Let's take it to full speed. And slowing down. Well, there was a slight weight gain. How about we reverse polarity? See if that had anything to do with it. There was a very slight weight gain over there of about 20 millinewtons, which would be equivalent to about 2 grams. And this is with a pretty weak magnetic field. Remember, we're only talking about 200 Gauss, which is less than the average fridge magnet. So in order to flip the magnetic field, we're going to we'll just flip the entire electromagnet. Now, if there is any effect, we will see it shortly. Okay, just like last time, I will start off by powering it up, the motor. Okay, we're turning on the electromagnet field in 3, 2, 1. Field is on. Powering down the electromagnet. I have to turn this up. I'm smelling something burning here from the motor. I think the wires are getting pretty hot from the load. There's an obvious burning smell going on here. Oh, it smells nasty in here right now. Okay, I'm going to stop the share. So what do you all think of that?
It was highly entertaining to watch, but I think it's pretty clear from just the motion of your sample above it that the airflow is the most significant contributor of anything that's going on here. So you did get about 2 grams of pull towards that disc as it was spinning after you lowered it down a little closer. But interesting.
Yeah, that's
And,
kind of what I figured also. That was my take, was that the disc is spinning there out to the side, right? And so
Yeah, there might be an airflow problem. I can try it again, but right now everything is pretty hot, and I'm smelling something burning. Oh yeah, it's the wire.
it's the wire
Wires
insulation
underneath are
probably.
starting to burn. They got so hot from the load. So
Yeah.
yeah, and it's also the plastic thing that we have on the table. So there is some obvious issues over there that we'll have to address. Also, the strength of the magnetic field is orders of magnitude away from what I would want to run such an experiment at. Was it 300 Gauss, which is 0.03 Tesla. Okay, I just shut that off. Any questions?
Yeah, sorry for joining late. What kind of materials are you working with there for your spinning disc?
Oh, the disc is 5052 aluminum disc.
So
it's not
your
like
test
the
sample above it is what?
The test sample above it is Teflon.
Okay, cool.
Right, and it's hanging about an inch and a half above the disc right now. So there is obviously concern of airflow. Although I did notice when I turned the electromagnet on, there was a change. Like when it was spinning, it was at one weight. When you turned the electromagnet on while it was spinning, there was another weight gain. But we shouldn't be seeing weight gains, really. We should be seeing something else. It's possible that what we really need is very powerful electromagnetic pulses, similar to the way what we're doing with dynamic nuclear orientation. We're dealing with a 4 millisecond pulse. So maybe we can set up some sort of system and get it in oscillation with a large capacitor bank and have the electromagnet basically pulse every 4 milliseconds back and forth at, whatever that frequency is. And I'm sure Jeremiah can help me hook up something like that if we wanted to pursue this in the future.
This was
Yeah,
this was Alzofon's homopolar generator, right? Wasn't it?
He alluded to it, but he never built it. So it's hard to say, whose exactly this belongs to, but it is what we're seeing in the core of the ARV, at least the basic setup. We don't know the electronics and the exact, configuration of the electromagnetic fields.
Oh, okay.
So this is basically what we're seeing in the core of the ARV.
Well, what I'd recommend is, first off, get a few more digits on your scale, and then secondly, put that test sample inside of a closed box where the scale is located. You could use one of your higher resolution scales. You have better scales if you place it underneath something instead of, say, above it. Or you could even place your better resolution digital scales above the thing and then hang it from a platform. That might be another way to do it, since with your vernier scale, you don't have that really high resolution. You're only at 1 gram, and you're probably looking for fractions of a gram here.
I would hope we're not looking for fractions of a gram, because this effect wouldn't be very useful if it's just fractions of a gram.
Well, maybe it's useful under a few Tesla with a superconducting magnet, but maybe under this kind of magnetic field, we only get a few fractions. But at least you'll be able to see it. Right now, we're kind of blind.
Right. How would you recommend pulsing a coil like this?
You could pulse it with the equipment you already have, using your Thyrotron or using an SCR or using a mechanical switch. But really, I think for the coil setup on this, instead of the single coil like we have right now, you already have that, and that's nice. Make a duplicate of it so that you can set yourself up with a dual coil setup. And you get, by spacing these two coils apart at some distance, you're going to get a lot better flux coupling and a more uniform field. Helmholtz coils, they're called. So just replicate that and space them about 4 to 6 inches apart.
Okay. Also, I was considering actually pulsing the fields using some sort of capacitor and coil combination.
In this case, you're probably better off to try it and actually see that measurement by pulsing it quickly and with less energy, as compared to a very high energy impulse where you're just going to get a single event and probably not be able to capture it.
Right. So we need a system that can pulse it every 4 milliseconds for several seconds, and
Right.
and preferably, not waste all that energy. So we want a way store it back inside of a capacitor, then have it bouncing back and forth, similar way you have a Tesla coil would work, just at a much lower frequency.
Yeah. Another mechanical way you could look for it is doing the same water reflection thing that we were looking for with Podklinov and Pour. That might be another mechanism to try and indicate very small amounts of force, as long as the tray is much, much wider than the disc and the magnet. So probably 1.5 feet by 1.5 feet or something, so that you can really see if only one area is distorted. If it does lose weight or if it gains it, it's either going to pull it down in the center or push it up in the center, but it shouldn't be affected everywhere else.
The idea of using water, because water is conductive to some level, and we're dealing with strong magnetic fields, so
Yeah, that's true.
yeah, there may be some interference. That's why.
What about oil?
Oil has very high viscosity, so it would be unlikely to see any ripples.
WD-40 doesn't. WD-40 is generally non-conductive and also extraordinarily thin, so you could empty a can of that in there or just use the liquid. That might work.
There also might not be a strong enough gradient to really see. You may be dealing with, just a 1% gradual rise. Even if there was a 10% weight loss in the center, it would be so gradual that it would be pretty hard to detect.
Oh no, if there's a 10% weight loss in the center, you'd see a huge bulge coming out there. It would be very visibly obvious with such a large percent. Even if it was 1%, you'd still see that. It'd be visibly obvious.
I'm not so sure about that, but hopefully you're right. Yeah, so that's something that we need to work on in the future, is making some sort of system that would allow it to be pulsed, because according to Alzofon, having a continuous microwave impulse on the sample will create a weight gain, which is similar to what we were doing over here with the constant magnetic field.
You've got that microwave horn still, don't you, Mark?
Oh yeah, we have lots of microwave horns.
You could try just irradiating that maybe inside your chamber there while you're spinning the disc.
This is nowhere near a strong enough magnetic field for those frequencies. This is 260 Gauss. We need to get to 2200 Gauss for that chamber. So that's going to be a totally different coil and setup. And we also need a resonant chamber to concentrate the microwave energy, which is something that we're working on, waiting for the machine shop to get back to us with the parts. And when that's ready, we'll have to do a whole bunch of testing in order to figure out whether it's in resonance or not. Just building the equipment to find out if it's in resonance has been a problem.
I guess you still have like a source though, like your microwave horn could be a microwave source for this. You could pulse that.
Right, but it has to be a
right?
frequency, which is correlated with the strength of the magnetic field. So at 300 Gauss, we're talking in the megahertz range, which is way different. That's RF. That's like ham radio frequencies. So it's a very different frequency range, and I'm not sure if there is a point at which you can no longer couple to the electron. If you go down to low enough frequency and low enough Gauss measurement, you might not be able to couple to the electrons along more precession at a certain point. So it's there might be a minimal threshold. And right now, the capabilities we have, I think Todd DeCiato is trying the megahertz range, so that's something that he can try. I'm trying the C band and the X band. C band, we have a Klystron, which is capable of like 3,500 watts output, and in the X band, the strongest thing we have is a 20 watt variable wave tube amplifier that is putting out around 20 watts. So those are the capabilities we have right now at the moment. And I think Wayne is also in the C band. He's trying a couple things, and also in the megahertz range, he's trying all different ranges of frequencies and Gauss readings in order to work it. He also did something in the microwave range as well.
Yeah, Wayne actually tested quite a few variations in the acoustic range down below 100 kilohertz with a much weaker field. So he was looking for different effects as well. But he's tried just about every range that he could access, and I'm sure if he had more equipment, he'd try them all.
Right. But there is always that a flying saucer incident where the AWACS plane was in close proximity to a flying saucer of such that, and they detected pulses every like 4 or 5 milliseconds at 2.995 gigahertz. And they said it seemed to be, connected to its propulsion system. So if they're using the gigahertz range, I would assume that there's a reason for that. Microwaves are less desirable for the human body than megahertz are, because megahertz are, they don't really couple to your body that well. So there's obvious health risks to using microwaves. So if they could have used megahertz, they probably would have, or it could be that you're looking at a harmonic. I'm not sure, but the only way to really know is to test, and that's what we plan on doing. Tim, I think you're muted.
Yeah, I am muted. How much more time do we have, or do you think I should stop recording for today? We're just about a little bit over 5.5 hours. The presentations that you guys did stole the show.
Oh yeah, it's too bad all the guys from England left. I do have a couple more pictures if anyone wants to see of us putting the lab together and all that stuff. If you're interested.
Well, it's up to you. Some of that stuff I'm going to put up on the new website, right? So.
Yeah, we'll probably put stuff up. I just wanted to show like how we built the lab and all that. That was actually fun. We turned a bedroom into a laboratory.
Honestly, I was most impressed by, I think the best part of today was your experimental videos. Just seeing you guys doing experiments with motion and sound and things moving, that's, you don't have to have a positive result. What it shows is you're doing the work and you're getting results, so.
I'd say that pretty well covered what we have for now. I mean, we're going to be doing a whole new series of experiments, and as we go on here, we're increasing the quality of the experiments. So a lot of these were just rough drafts, sort of running through the first iterations and learning what we needed to do. So when we redo these again in a month or two, we're going to know what we're getting into before we start, and we'll be able to build them up from scratch with much idealized characteristics.
Yeah.
But I'd say that we pretty well covered it for today.
Well, guys, let me shut this down for now. Then I'm going to stop.
Tim, hi Tim. Can I just jump in and suggest one thing, because I missed the I missed pretty much all the presentations, but the thing that they should watch out for in the experiments is that the field effects can take a lot of time to develop, and so if you're doing measurements and you're expecting something to happen, in the next minute, it might take 3 or 4 hours for the field to build up. And so I just wanted to mention that.
Okay.
That's a very good point. Also, Eric, would you expect any effect to happen here with just 300 Gauss, or completely out of range?
You broke up there?
I was saying, would you expect anything to happen with this experiment at just 300 Gauss, or are we like magnitudes off?
Honestly, about 20 minutes into your experimental session, I cut out. I was not able to. So I just jumped back on about 10 minutes ago. So I'm not even sure what you're referring to. So if you could send me an email, I'll talk to you that way.
You can check it out on the live stream on Jeremy's channel or on Tim Ventura's channel when he posts it. But we did. Yeah. It's right next to me, and we had a spinning aluminum disc inside of a magnetic field and weight loss was measured by a piece of plastic hanging above it. Because if there is dynamic nuclear orientation happening and there is a weight loss effect, it's supposed to be contagious and move around to surrounding objects. And what we did see was a weight gain, not a weight loss. So that is interesting.
Okay, well, in my thinking, that would correspond to the opposite of time dilation. So it would be a speed up in the clock rate. So let's, send me an email and we can talk about it.
Okay. Will do.